Hello and welcome to this film which concerns itself with the analysis of mass spectra. So hopefully you've just seen the film about how a mass spectrometer works. Now that we know how it is that a mass spectrometer is producing these graphs or this information that it outputs, we're going to use the data from a mass spectrometer to try and find out about the relative abundance of isotopes and also to calculate the relative atomic mass of an element, that is to say the average mass of an atom. Okay, so let's start off by looking at carbon and what a mass spectrum of carbon would look like. So in other words, if I took a sample of carbon and put it in my mass spectrometer, which I don't have at home because they're very expensive machines, but here's what the mass spectrum would look like, and we can see that there would be a very high intensity at a mass charge ratio or atomic mass unit of 12, a very small peak at 13, and although we can't really see it here, a very, very tiny peak at 14. And that's because carbon has 3 different naturally occurring isotopes, and we can see here their percentage abundances. Okay, and as well as that, we can see what's in their atoms, but we should be able to figure that out by now. Okay, now if we want to calculate the relative atomic mass of carbon, that is to say the average mass of a carbon atom in atomic mass units, so that is to say relative to the mass of a carbon, an atom of carbon-12, we've got to not only find the average mass of all the isotopes, which would obviously just be 13, but we've got to take into consideration the percentages of them. Now, if you had 100 of these atoms, you could easily find their average mass because you'd know that 98.9 of them, although I suppose that doesn't really make sense, but 98.9% of them, so 98.9 out of every 100 would have a mass of 12. And then there'd be 1.1% of them that would have a mass of 13. And there'd be less than 0.1%, so we're saying this is insignificant, as we can see here. These two add up to 100%. But basically, if I've added all these masses together, then I've had to count 100 atoms. So to find the average mass, I'm going to take these percentage abundances, multiply them by the isotopic masses of the isotopes, and then divide by 100. And if I do that, I'll find that I get the value 12.011, which is what it says on our periodic table for carbon. And that is to say that this mass here is a weighted average of all these isotopes. So it's not just the average of 12, 13 and 14, but the average mass of atoms taking into account what their relative abundances are. Now that was an example using percentage abundances, but let's say that our output had been in relative abundance, and so my mass spectrum had a peak at 6, it had a peak at 7 because I was looking at lithium this time, 2 different isotopes of it, and one peak was very smallish, one peak was quite large, but instead of percentage on this axis, it had relative abundance, and it was reading out 11.1 for that one and 0.9 for the other. Now, how would we deal with this problem? Well, there's lots of different ways, well, not that many really, but we could find these numbers as a percentage. So we could say, what is 0.9 out of 12 as a percentage? Or we could just say to ourselves, well, what do these numbers add up to? And we could see that that would be 12. And that would mean that 0.9 out of every 12, so 0.9 atoms out of every 12 would have a mass of 6, so 0.9 times 6, plus 11.1 times 7. How many atoms have I used in my average? Well, 12. So I'm taking these relative abundances, I'm adding them up to find what number to put on the bottom here, and I'm multiplying the relative abundances by the masses. So it's rather like the problem with percentages, and if I prefer, I could turn these two numbers into percentages before I start, okay? But there's no need to. It's a little bit less work to do it this way, and if I calculate that number, what do I get? I get 6.925. Now it's important to realise that this might be slightly different to the value on the periodic table, and if we get asked one of these questions in a test, we shouldn't just go and look up what it says in the periodic table because we might get a slightly different answer. Anyway, so we've now looked at 2 different ways of going from relative abundance to a relative atomic mass, that is to say an average mass. Now we're going to kind of turn the problem on its head, and we've got the relative atomic mass given to us here, this 186.2 for rhenium. And we're told that there are two different isotopes of it. So now our job is to find out what the relative abundance of these isotopes must have been to give us this relative atomic mass. Now let's deal with these things as percentages. Okay? Now if I don't know the percentages, I could say that the percentage of 185 atoms would be X. So 185 times X% of that isotope plus 187 times, well, what would the number of 187 atoms be? Well, if I'm talking in percentage terms, then that would be 100 minus X. Okay, and then if I'm doing it in percentages, then I've got to divide by 100 to get this number 186.2. Okay, so now my problem is simply to solve for X. So I'm going to take this 100 over there, and I'm going to find that 185X minus 187X plus 18,700 is equal to 100 times that, which is 18,620. Okay, now I'm going to say, well, that's just minus 2x, and I'm going to take this over to this side and subtract it from there, and that equals, just done this before, so that's minus 80, and therefore x is 40. Now remember, what was x? Well, x was what I decided I would call the percentage of 185 atoms. So the relative abundance of these things, 185 rhenium has a percentage abundance of 40%, and 187 rhenium has a relative abundance of 60%. Okay, so two different types of problem there. I suppose three, if we say that there are different ways of giving us the relative abundance in a question, but we can use the mass-charge ratios, so that is basically the masses of the particles, or the masses of the isotopes, and their relative abundances, given to us in different ways, to calculate the relative atomic mass. So that's the first two problems that we did. And we can use atomic mass data, so if we're told the relative atomic mass of an element, we can predict the relative abundance of the isotopes of that element, so long as we know what the isotopes were. Now hopefully that makes sense. If it doesn't, or if you've got any questions or comments, then please feel free to come and see me or to post a comment on YouTube.